Okay. So inter-process communication, there are two main methods for inter-process communication. Of course, when we create multiple processes to do something useful, usually we want them to communicate with each other. So we don't just create independent processes. At least, if these two processes belong to the same application, then they have to communicate, and we have to synchronize them. We'll talk about synchronization later. But let's now understand the difference between shared memory communication and message passing, the two main methods of inter-process communication. In message passing, you have two processes in this example, process A and process B. So this is the address space of process A, address space of process B, and this is the address space of the kernel. Messages are managed and maintained and hosted by the kernel. So the messages themselves, everything is in the kernel address space. Okay? In that memory block that belongs to the kernel. And whenever a process needs to communicate with another process, it's going to have to go through the kernel, and this means making a system call. So a send or a receive is a system call. Okay, so every communication, every message that gets sent or received goes through the kernel. Now in shared memory, it's a totally different scheme. So in shared memory, you have two processes in memory, process A and process B. And one of the processes creates a shared memory block. And that shared memory block physically belongs to the address space of one of the processes, usually the process that creates it. So suppose that here process A creates a shared memory block. That shared memory block will be put in the address space of process number A. But it will be a special memory block that, under system control, can be accessed by multiple processes. So remember, it's the system's job, the kernel's job, to do memory protection and prevent a process from accessing the address space of another process. But shared memory, by doing shared memory, you are asking the system to make an exception, or you are asking the system to. You are telling the system, okay, this memory block is in my address space, but other processes are allowed to access it. So through the system, of course. So the system is giving other processes access to this memory block. Okay, so it's like overriding protection only for this particular piece of memory that is shared memory. But now the good thing about shared memory is once the kernel sets up the shared memory block, the kernel does not intervene anymore. So unlike message passing, in message passing there is kernel intervention with every message. But with shared memory, once the kernel sets up the shared memory block, no kernel intervention is needed. And the kernel has nothing to do with the format of this shared memory block. So the user processes that are communicating through this shared memory, they will define their own their own shared memory format or their own communication protocol. So if you have a producer and a consumer, like we will do in assignment number 1, there is a certain format that we define, we as application programmers. So the producer writes the data to this buffer in a certain format, and the consumer knows that format. And knowing that format will allow it to consume that data or understand what's in the shared memory buffer. So this is controlled by the processes. The format and how the communication is done is controlled by the processes. Now, given this description, which do you think will be faster, message passing or shared memory? Yeah, shared memory will be generally faster, but in certain cases, on a multi-processor system, because of cache coherency problems, shared memory may end up being too slow that it may end up being slower than message passing. And let me explain cache coherency, the cache coherency problem. Cache coherency is something that is handled by the hardware. So the hardware implements its own cache coherency protocol, but that's going to slow shared memory communication, because if you have CPU 1 and CPU 2, and each CPU will normally have its own cache. So this is the cache, and this is shared memory. So normally, each CPU will have its own cache. This is a multiprocessor system. Each CPU has its own cache, and there is shared memory. Okay? And suppose that we have multiple memory locations. Suppose that we have a memory location here with value 7, and then both CPUs load this in their cache. So now this has 7, and this has 7. Now what if at some point CPU 1 modifies this 7 and changes it to 19? Okay. Now what's the problem that we have?
CPU doesn't have the latest.
Yeah, so the shared memory and CPU2 do not have the latest. Of course, the hardware ensures correctness. So when CPU2 tries to access this 7, the hardware will recognize that this 7 is outdated because the other CPU has modified that in its own cache. So the hardware will detect this, but the hardware will not have a magical solution to this. This is going to take time, because in order to resolve this, the hardware will have to first copy this into memory, update memory, and then load this into here with the updated 19. Now this update, to ensure cache coherency, this will take some time. It's not going to happen in 0 time. And now, if you can imagine how slow this will get if you have many processors. So if you have a system with many CPUs, many CPUs, this will become slower and slower. So it may get slow to the degree that message passing becomes faster in that case. Okay, so this is the concept of cache coherency and why it may slow shared memory on multiprocessor systems.